You ever stop and wonder what could possibly connect the salad dressing in your fridge, the paint on your walls, and get this, the actual blood running through your veins? Sounds kind of crazy, right? Well, the answer is surprisingly simple, and it all comes down to the amazing world of tiny, hidden mixtures.
So let's just take a look at these three things for a second: milk, mayonnaise, and paint. I mean, on the surface, they couldn't be more different. But deep down, scientifically, they're all built on the exact same secret principle.
And here's the secret. They are all what we call emulsions. An emulsion is what you get when you take two liquids that absolutely refuse to mix, like oil and water, and you force one to break up into these microscopic droplets that just hang there, suspended in the other. It's like a stable but, let's say, unwilling partnership.
So let's start by diving into this world in a drop. We're going to see how the science of emulsions turns all these everyday items, from the food we eat to the supplies in our house, into these stable mixtures we totally rely on.
Next up, we're going to get into how this all actually works. Because, knowing what an emulsion is, that's one thing. But how do you actually force two liquids that pretty much hate each other to mix and, more importantly, to stay mixed?
Well, it turns out there are two basic ways to do it. You can have tiny little oil droplets scattered around in water, and that's how you get things like milk. Or you can just flip that whole recipe around and suspend tiny water droplets in oil, which is the secret behind things like butter and even those heavy industrial greases. Which, of course, brings us to the really big problem. We've all done this, right? You shake up some oil and vinegar, and for a second it looks mixed, but then it just separates right back out. So how do you stop that from happening? How do you create a permanent peace treaty between these two? The whole process is called emulsification, and it's kind of like a three-step dance. First, you start with your two liquids. Second, you blend them with a ton of energy. It's a process called homogenization that shatters one of the liquids into billions of tiny droplets. But the real magic, the secret sauce, is in step 3. You add a special ingredient called an emulsifier. This emulsifier, it's like a molecular peacemaker. Its molecules grab onto those tiny droplets and coat them, which stops them from clumping back together and separating out. And what's wild is what can be an emulsifier. I mean, sure, we expect things like soap or gelatin, but even superfine powders like clay or lamp black, which is basically soot, can get the job done. So, we've seen how this works in the kitchen, but this whole principle goes way, way further. Emulsions are actually part of a much bigger family of mixtures called colloids. And trust me, once you start looking for them, you realize they are absolutely everywhere. The scale of this is just staggering. I mean, inside your own body, your blood is a colloid. In medicine, a whole bunch of drugs are delivered this way. In industry, yep, synthetic plastics, silicones, rubber, they're all colloids. Even nature is in on the game. From the tiny particles that make the sky blue to the slow, steady buildup of river deltas. But maybe the most incredible application of all is the one that's happening inside of you, right this second. So let's take a closer look at what we can call nature's tiny, perfect machines. We are talking about enzymes. These are these incredibly complex protein molecules that exist in, you guessed it, a colloidal state, just floating around inside our cells. Their whole job is to act as catalysts, to make the chemical reactions that keep us alive happen at unbelievable speeds. And when I say unbelievable speeds, I mean it. The efficiency is just mind-blowing. A single enzyme molecule can process up to 1 million other molecules every single minute. Without these guys, the reactions we need to live would be way too slow to even sustain us. Okay, so that raises the obvious question. How? How are these tiny colloidal particles so unbelievably powerful and efficient at what they do? This chart really shows you the secret. Think of every chemical reaction as needing a big push to get started, an activation energy. Without any help, this particular reaction needs 18 units of energy. Now, an industrial catalyst like platinum helps, bringing it down to about 11.7. But just look at the enzyme. It drops the energy needed to less than 2. It doesn't just speed the reaction up, it makes it ridiculously easy to even get started. Now, this incredible efficiency isn't some kind of magic. It actually comes from a really elegant and beautifully simple mechanism, which we're going to explore in our last section here. You see, an enzyme's power isn't about brute force, it's all about precision. Their true genius is that they are incredibly, fantastically specific about what they choose to work on. It all boils down to the famous lock and key idea. Just imagine every enzyme has this uniquely shaped docking area called an active site. And only one specific molecule in the whole body, the substrate, has the exact right shape to fit into it, like a key into a lock. Once it's locked in, the enzyme does its chemical magic, transforms the substrate, and then releases the new product, completely unchanged and ready to do it all over again.
This is exactly why an enzyme like urease is an absolute master at breaking down one thing, urea. But if you give it something that looks almost the same, it won't even touch it. The key just doesn't fit the lock. It's the ultimate specialist.
So let's bring this all full circle. Just think about it for a second. The very same scientific principle of suspended colloidal particles, the one that keeps your mayonnaise from separating back into oil and water, is exactly what allows these microscopic machines, these enzymes, to float perfectly inside your cells, carrying out the millions of reactions every single second that keep you alive. From the dinner table to your own DNA, it is all connected.
So, from the grand scale of nature all the way down to the microscopic world inside each of us, it's pretty clear that our world is fundamentally built on tiny mixtures. And now that we understand this powerful principle, the real question is, what are we going to build with it next?